nombrado miembro de número de la Academia de Ciencias de Colombia. Está festejando hasta ahora su suceso. También tenemos a Felipe Mundaca, de la Universidad de San Sebastián en Puerto Montt, Chile, pero no se conecta aún. José Fermín, de la Universidad de Zulia de Venezuela. José. Felipe Mundaca, ¿de dónde estás?
¿Se escucha, Luis?
Sí. Sí.
Bom
Perfecto.
dia, Sergio.
Bom dia, José. Tudo bem?
Tudo bom.
Perfecto. Bien, entonces hay más panelistas que se van a ir incorporando seguramente durante la palestra. Bien. En la foto, nuevamente a los que ya estamos en línea, a los que se están conectando recientemente, en la foto se encuentra el profesor Sergio Rezende de la Universidad Federal de Pernambuco. También se encuentra el profesor Ángel Bustamante de la Universidad de San Marcos, que ahora es decano de la Universidad, de la Facultad de Ciencias Físicas de la Universidad de San Marcos. El doctor Daniel Reyes López, del Instituto Militar de Río de Janeiro, y también está afiliado a la Universidad de San Marcos, en Perú. La candidata doctora Silvia Maricela Espinosa Suárez, también de la Universidad de San Marcos. Albino, por favor. Y también, ¿quién es? También yo estoy aquí con varios kilos de menos, cuando era flaco. Perfecto. Bien, entonces el día de hoy tenemos al profesor Albino Aguiar, que va a ser o moderador. Bienvenido, Sergio Rezende. Bueno, entonces, Albino, te dejo la posta. Obrigado.
Gracias, Luis. Bueno, buenos días, bom dias, good afternoon, dobra bem. What more should I say? Sérgio, bem-vindo. Bom, Luiz é o secretário-geral da rede, então quem manda é ele, certo? Ele já apresentou. Eu vou mencionar formalmente as universidades que constituem essa rede. Essa rede é a Rede Latino-Americana de Física da Matéria Condensada e Ciência de Materiais. É formada pela Universidade Maior Nacional de São Marcos, em Lima, que é a decana das Américas, a Universidade de Barranca, as duas no Peru, Universidade Nacional de Colômbia, em Bogotá e em Barranquilha, e a Universidade del Norte, da Colômbia, a Universidade del Zulia, em Venezuela, o Centro de Investigações de Materiais Avançados no México, Cinvestaf, no México, a Universidade Católica del Norte, em Antofagasta, Chile, a Universidade de San Sebastián, em Porto Montt, Chile, University College, London University of Cambridge, a Universidade Federal Rural de Rio de Janeiro e a Universidade Federal de Pernambuco. Então, it's our pleasure having you here. We are very glad. And I'll now say some words about Sergio. Normally, as I said several times, I use to announce the speaker more or less like this. Those who not know Sergio Rezende are not in the panel. Yeah? Sergio is my colleague since long time. he had very black hair, me too, that time. And he's a very known scientist in Brazil, in the world. He used to be the Minister of Science, Technology, and Innovation in Brazil several years ago, or some years ago. He's emeritus professor of the University Federal de Pernambuco, and he likes a lot to work because he is already retired a long time ago, and he continues to work almost every day he goes to the university. It's really a pleasure to have you here, Sergio. Now it's your turn.
Thank you, Albino, for the invitation to speak to this important network, and thank you for your for the introduction. Thank you, Luis, for the previous introduction of the panelists. Let me ask you, Luis and Albino, should I speak in English or in Portuguese? I cannot speak Spanish.
In which you feel much better. Here also panelists in English who speaks English as well.
Okay. You can speak in Romano. Okay, it's good for you.
I'll speak in English because the slides are in English, except for the first one. The title that I presented, that I proposed, is in Portuguese. But let me speak in English, since I see some English-speaking people like Stuart Holmes, who probably doesn't speak Portuguese or Spanish. Let me share the screen.
No, we are not seeing.
Just a minute.
Oh, no, it's coming.
Just a minute. It takes
okay.
I'm just trying to hide this bar here because it's in the middle of my. Okay, let's go. As I said, I wrote the title in Portuguese, but it's clear what it means. Spintrônica, Fundamentals, and Recent Advances. Something happened, I cannot move the slides.
Maybe right click and activate maybe the pointer.
Okay, now we go. Since some people here don't work with magnetism, I'll present very basic information. As you know, electrons, beside the charge, they have spin, and associated with the spin, they have a magnetic moment. So the spin can be acted upon by an external magnetic field. If the electrons have spin, the atoms also may have spin, depending on how many atoms they have in each shell. And the atoms or ions of some elements, they have a total spin, and so they have atomic magnetic moments. These atomic magnetic moments are the ones that give rise to the magnetic property. Strongly magnetic materials have an interaction between neighbor spins, and this interaction then makes the materials ferromagnetic, anti-ferromagnetic, ferrimagnetic, and other more complicated arrangements, spin arrangements. So in the periodic table that I show here, there are several elements in the iron transition group, like vanadium, chromium, manganese, iron, cobalt, nickel, that before, when they lose some electron to become an ion, they lose electrons in the outer shell, and they keep the 3D shell unfilled. An unfilled shell has a net spin, then a net magnetic moment. This also happens to some of the elements of the rare earth group here. So these materials have magnetic properties, and there are traditionally materials, classic materials, are classified in 3 different categories. Soft magnetic materials are those in which the hysteresis cycle, the response of the magnetization as a function of an applied magnetic field. As you know, it has a hysteretic behavior, but some materials, the magnetization, demagnetization occurs in curves that are very close together. These are called soft magnetic materials, and they are used in transformers, in motors, in magnetic heads, many applications. Hard magnets are materials that have a wide and high hysteresis cycle. So when the material is magnetized and the external magnetic field is left out, the magnetization remains with some value that depends on the materials, and this is called then a hard magnet, permanent magnet, and materials of this type are used in generators, motors, loudspeaker, microphones, and so on. This has been used in technology for almost 2 centuries. And there are materials used in the last century that have an intermediate hysteresis cycle. They are used for magnetic recording. That is, if you apply a magnetic field, the material in some region, the material remains magnetized in that region. And then if you remove the magnetic field, the material retains the magnetization, so it stores the information. In a binary system, in computers, it can be magnetized in one direction or in the opposite, like here. And this means that the material can be used for digital storage. Well, one example of the evolution of the properties of material in the last decade. As I said, a hard magnet has a large hysteresis cycle, and usually it is characterized, the parameter that characterizes material, hard magnet, is the so-called BH product. If we fit a rectangle here, the higher or the broader the rectangle, the better its property. So the product is an indication of the property. I show here what happened in the last 50 years with the BH products of material used as permanent magnet. As time went by, the work of physicists, material scientists, engineers, and so on, gradually developed material rare earth elements and the BH product increased. And as you see, it increased by a factor of over 6 or 7 in 70 years. And today, neodymium iron boron magnets are used to produce magnetic field and flux. And this allowed us to make devices with smaller and smaller magnets to produce the same effect. And this is what made possible the use of practical wind turbine. The wind turbine requires a generator. The generator has to be placed in a top like this, in a post like this. And 50 years ago, they were not practical because the generators were very big. With the development of rare earth magnets, people were able to make smaller generators, and today we have turbine with over 3 megawatts of energy generation. And of course, this also made possible hybrid cars and the electric motor cars that are real, and they will certainly dominate the market in a few years. Well, magnetic recording here, also involved technologies that evolved along the decades, and hard disk drives became important in computers in the 60s, and in more recent years, Spintrônica made possible the manufacturing of hard disk drives with smaller and smaller reading head, which made possible to have disk drives with larger storage capacity. And Spintrônica is the area of physics and technology that makes use of the electron spin to perform new functionality. And note that the electron spin is the natural carrier of digital information. Spin up could be 1, spin down could be 0. So there are some advantages of using the electron spin for processing digital information, but there are many other properties that make this field very active in the past decades. To understand very basic why Spintrônica was not used before, let's consider material that has dimension much larger than the mean free pair. If you have electrons moving in this material, since the mean free path is small, the electron will undergo many collisions from here to here. And in each collision, the electron loses the information of the spin. So that's the reason why in conventional electronics, the spin is not important. Now, if we have a multi-layer material made possible by nanotechnology, then we can have the following: an electron flowing through a multi-layer. During the transit in the magnetic material, it doesn't undergo collision because the distance is much smaller than the mean free path. So while the electron is here, it can be controlled. Its motion, its property can be controlled by the spin. So its use of thin films with thickness much smaller than the mean free path made possible which is called spin-dependent transport. The transport is governed, can be governed by the spin that can be affected by an external magnetic field or some other effect. So the first important discovery, actually the most important discovery in spintronics until now, was the giant magnetoresistance. This was discovered by two groups. One group was the group by Albert Ferre in Orsay, in France. But the first author of the paper on giant magnetoresistance is a Brazilian, our colleague Mario Baibich from the Federal University of Rio Grande do Sul. What is it that they did? Mario was a postdoc in Ferre's group. They measured the resistance across the multi-layer that was made in such a way that neighboring magnetic layers have the magnetization in opposite direction, like this. This can be controlled by the thickness of the metallic interlayer. So what they did was to measure here different multi-layers with different thickness of the chromium spacer. By applying an external magnetic field, the resistance change, and the change was very large for a chromium interlayer with thickness 9 angstrom. That the electron spin here in the explanation I already mentioned. It's in a simple device. Yes. This is a magnetic layer, like iron, thermalloy, nickel iron, or cobalt iron. And this is another magnetic layer. Between them, there is a non-magnetic layer, for example, copper. This layer here is placed in contact with an antiferromagnetic material. And this produces an effect that is called exchange bias. The magnetization of this layer is pinned. It's attached to the magnetization of the antiferromagnet of the last layer by the exchange interaction. And this layer is called the free layer or the sensing layer. So if an external action makes the magnetization to be in this direction, it is aligned in the same direction as the reference layer. And then as the electron moves through the copper layer, the resistance is smaller because the spin, as it goes to the interface, it sees a magnetization with the same direction in both layers. So resistance is smaller. Now, if we move the magnetization to the other direction, then the electron has some spin, as it touches the interface here, it sees a magnetization in one direction. When it touches this one, it's in the other direction. And this causes larger resistance because there's a spin-orbit coupling. Spin-orbit coupling is a very important concept in our spintronic phenomena. I'm going to mention some a little later. So this layer here is a sensing layer. It can, depending on the magnetization, the direction of magnetization, or here, it will produce a different resistance, and therefore we can put this in the sensing layer of a magnetic recording medium. What is the advantage of this? The advantage is this traditional conventional recording used as detection the Faraday effect. Now, the Faraday effect requires flux to induce a voltage. And flux requires area, volume. So, magnetic recording conventional reading had a problem with that. The bit for magnetic recorder had to be large because the flux had to be large. Now, the case of this so-called spin valve sensor, the spin valve sensor is sensitive to the magnetic field, not to the flux. So a small magnetic field, few Erston can very easily change the magnetization of the sensing layer, and then it changes the resistance. So if we have a reading current here, the voltage will depend on the resistance, and this is a simple detector for the direction of the magnetization. The introduction of magnetoresistive head and giant magnetoresistance head changed the magnetic industry. You see, the vertical axis here is in a log scale. And as you can see, the introduction of magnetoresistance had changed the slope of the evolution along time. And this made possible hard disk drives, very large capacity, because this made possible smaller and smaller sensing heads. This discovery was so important that for basic physics and also for application, that Albert Fecht, I mentioned, was one of the authors of that first paper, together with Peter Grimberg, who published, had an independent research, published independently of Fecht. They won the Physics Nobel Prize in 2007 because their discovery made possible a revolution in technology besides a scientific revolution. And it was the origin of the field of the spintronics about 30 years ago. So this is a newer field in magnetism, relatively newer. The LF phenomena studied in magnetic multilayer involved properties of single films, the exchange via effect, interlayer coupling between layers, giant magnetic resistance, spin valve phenomena, spin transfer torque, magnetic tunneling. And intense research took place in the 90s to understand many phenomena here. There are still much activity in these fields, but then about 20 years ago, newer areas of spintronics came along, involving spin currents. I'm going to speak about spin currents, spin pumping effect. I don't have the time to speak about spin electronics, but I'm going to speak about spin electronics and about spintronics in 2D materials. I should mention that we began our work in the 90s, working with the alien phenomenon, films and multilayer, and José Fermin, who is with us today here, now at the University of Julia. José Fermin was the main author of two well-cited papers, Magnetic Properties of Titanium Iron Double Layers, and also ferromagnetic plasma unwritten and especially thin iron films. We bought a system for sputtering deposition just before Jose came here for the PhD, and then he was involved in making the materials together with Yao Li, a Chinese who spent a couple of years here. And in our group, then we produced several papers in the LFNO. Well, this introduction was a long one, took me half the talk, but I think it was important for you to have a grasp of some basic phenomena. And I'm going to continue on the basic information, and then I'll go fast through several phenomena just to show you the richness of the field. I will not have the time to go into detail in each one of them. To understand what spin currents, which is a relatively new phenomenon, although it was proposed almost 30 years ago. Let's take a thin layer, metallic layer. And this is a very simple illustration made by my colleague Antonio Azevedo of the flow of electrons, assuming that there is no collision. So this is a very hypothetical situation. Since electrons have spin up and spin down, assuming that they move uniformly, they are producing here a charge current, which is the sum of the current of electrons with spin up and electrons spin down. If we subtract the two currents, we get zero. And the subtraction of the two currents is what we call spin current. Let's see the spin current here. If we have electrons with opposite spins moving in opposite directions, then we have zero charge current, but we have a spin current, because the spin current, the difference between electrons spin up and spin down. And this is different than zero. This is somewhat similar to what happens in a semiconductor that has electrons and holes. If we have electrons and holes moving in opposite directions, their charge current add, and it's the sum of the two currents, and we have non-zero charge current. However, if electrons and holes move in the same direction, we have zero charge current. So this is an illustration, a very schematic illustration of a spin current in a metal. Spin currents also exist in ferromagnetic insulators, but I will not have the time to speak about them. They involve magnons, magnon accumulation, magnon current. Now, a very important effect, which was predicted theoretically and took a few years to be detected and became a very important one, is the spin Hall effect. The Hall effect, all of you know from basic physics. The spin Hall is the Hall effect with the spin, which is with this. We have a charge current in a metallic layer. We are looking at the layer from the top, let's say. If we have material, heavy metal like platinum or palladium, they have a strong spin orbit property. So the collision of electrons in the material will be sensitive to the spin orbit. This means that electron will spin up, will be deflected upwards because this produces angular momentum up, and the electron will downspin will be flipped downwards because the angular momentum is in the opposite direction. And notice that here we have a spin current. So the charge current here has been converted into a spin current. So the spin Hall effect, which was actually predicted in a paper which is not easy to read, and it was hidden in the Soviet literature, it was rediscovered by Jorge Hirsch, an Argentinian who has been in the United States, in San Diego for a long time. Hirsch gave the name spin Hall effect. So the spin Hall effect is simply a Hall effect that is sensitive to spin that should occur in any metal that has a strong spin orbit couple. And this occurs in heavy metals, like, as I said, platinum, palladium, tungsten, and so on. The spin current can be represented by a spin current density. It's proportional to the charge current, and it's perpendicular to the two. It's represented by this cross product here, sigma cross J, and this is a parameter that says how strong is the effect. In platinum, the spin Hall effect, the spin Hall parameter is 0.05, which means 5%. There are materials that we know today that have 50%. In other words, half of the electrons in the current are deflected to produce a spin current. Another effect that was predicted theoretically a few years later was the spin pumping effect. Another very important effect in spintronics that also allows to generate a spin current. The authors were Bratas, Cerkovignac, Bauer, Halpring. This is a Norwegian, Ukrainian, Dutch, and American. That's a multinational group that predicted the following, proposed theoretically the following. If you have a ferromagnetic layer that it undergoes ferromagnetic resonance, the magnetization processing, by means of an external drive processing about the magnetic field. And if there is a metallic layer attached, deposited on the ferromagnetic layer, the magnetization procession actually carries angular momentum, and the angular momentum is injected in the interface. So across the interface, a spin current is generated. And this spin current diffuses and decays because of diffusion. That's an effect that always occurs in charge transport. But the important thing that they did is the following. The spin precession produces a spin current, and the spin current carries out of the magnetic layer angular momentum. So it's a damping mechanism. It produces damping of the magnetization motion. How can we see this experimentally? We have a ferromagnetic material. This can also be done in very magnetic materials and also in anti-ferromagnetic materials. We apply a magnetic field and we apply a driving field, microwave, for example. In anti-ferromagnets, people are using terahertz radiation, very high frequency. And then the magnetization will process, and this can be done placing a ferromagnetic sample inside a microwave cavity or a microwave device. that we place between the poles of a magnet. That's a microwave generator. The microwave comes here, and we observe the reflection. And there is a natural frequency here, which is the resonance frequency. So when the driving field has the frequency of the natural frequency, we have a resonance. Since we normally observe this by modulating the magnetic, what we see is the derivative of the absorption peak. The absorption peak is nearly a Lorentzian, and here is a Lorentzian derivative. This is the paramagnetic resonance spectrum of a simple permalloy layer film. Well, how about the spin pumping? The first detection of the spin pumping effect was actually made here in Recife, an idea of our colleague Antônio Azevedo. We observed the effect, but we did not understand everything involved. So the paper was presented in a magnetism conference with the title Evidence of the Spin Pumping Effect, with a question mark, because things were not very clear. What is the experiment? The experiment was done with a tri-layer, two magnetic layers and having a non-magnetic layer between them. And then Antonio had the idea of putting two contacts at the end of these structures with a few millimeters of dimension. And this is the FMR signal that I showed before. Now, by measuring the voltage between the two contacts, they measured, I see they because I was in Brazil at that time, just following their work. I was not so much involved. I only participated in some discussions. But the voltage gave this incredible result. A Lorentzian line with at the same field of the resonance. Of course, we conclude the experiment was done also with different materials. Only heavy metals had a strong voltage. Copper had a very small voltage. And we concluded that this was an evidence of the spin pumping effect predicted by the multinational group. But we could not understand how the spin current generated a voltage. For this reason, we had the question mark. The explanation came a year and a half later by the group of Saito, Japanese group that has been very active in Spintrônica. And the explanation is simple. It's the inverse of the spin Hall effect. I showed the spin Hall effect before. Electrons up and down spin moving in a current. They deflect like this. Now, if the electrons come in opposite direction, as in a spin current, now they will move toward the same edge because angular momentum here will couple with the spin up. Angular momentum here will couple the spin down because the two angular momenta have opposite direction. So this is the explanation of the voltage. We missed the explanation because, in fact, we did not know the paper by here. It was a theoretical paper in the middle of the physical review letters, in the middle of the library. At that time, we did not have access to the literature like we have today. We had to go to the library and keep reading the papers. And, of course, we miss many papers because of this. This effect, spin Hall effect, direct or inverse are basic effects for spintronics, and there are good reviews of these effects. The one by Axel Hoffman and one by this multinational team. But there is another effect that became important in the last few years. The spin charge conversion to this system. There are also some reviews of this. This is a review in which the most important author is Albert Fecht, published in Nature in 2016. The idea is this: if we have a two-dimensional system, and if the system, or if we have a two-dimensional system, as you know, electrons have an energy momentum curve that is a parabola, as I show here, because of the k square here. Now, if there is a spin-orbit coupling, we have to add to the Hamiltonian k dot gradient of the potential, that is the electric field, and this produces a splitting of the two bands. If we see this in three-dimensional, we actually have this paraboloids, which are split, and in one paraboloid, the spins have, the electron have spin pointing tangential like this, and in the other, the spins are like this. So if we have a cross-section, and if we plot this cross-section in a plane, what happens is that electrons here have spin up, and electrons here have spin down. Here means kx positive. If electrons move along plus x, they will have what is called spin momentum locking. And the spin momentum locking can produce very important effects. One effect was predicted by a Russian in the 80s, based on the Rashba effect. And this is called the Rashba-Edelstein effect. I'm showing here again two Dirac circles, one with the electron up. So if Kx is positive, we're going to have electrons in the outer Dirac circle up, and in the inner Dirac circle down. So now, if we produce a charge current, we have a displacement of the two circles, electrons spin up and down. Now, the displacement of the two circles will change the density of electrons in such a way that now we have a net spin polarization. This was the effect predicted by Edelstein. We have a current in a film with Rashba effect. This produces a spin polarization. And of course, if we have the opposite effect, if we impose our spin polarization in a 2D system with spin-up coupling, it will produce a current, because charge current, because it will displace the Dirac circle. The charge current is simply proportional to the spin current, but the spin current is a three-dimensional current going through the plane, and the charge current is a surface charge current. So one is proportional to the other, and this parameter has the dimension of length, because we have two different currents here, and this is called the IRE parameter that is proportional to the Rashba parameter. To show some experiments, I still have 15 minutes, 10 to 15 minutes. I'm going to rush to the experiment. Many experiments were done with a very important magnetic insulator, yttrium iron garnet. It's a material with a complicated unit cell, many atoms, but has been very basic for the study of many phenomena in magnetism and in recent years for insulator spintrônica. YAG is a material that has application in microwaves and also in infrared optics. YAG is very much used today for making spin pumping experiments. Let's say that we take a YAG film. The YAG film can be done by sputtering, but also can be done by other techniques that produce very good single crystal film. We deposit, for instance, a platinum layer on top of this. We do ferromagnetic resonance. Here is the ferromagnetic resonance response. It has several peaks because YAG has a very small damping. Because it has very small damping, it has waves, spin waves. And the spin waves produce standing waves. When we put platinum, all peaks broaden because of the spin pumping damping, but we detect very clear and strong. Notice that this is measured directly with a voltmeter. There's no noise here practically. This has several microvolts of intensity, and if we have the magnetic field in this direction, we have a positive peak. If we reverse the magnetic field, we reverse the polarization, and then the cross product of sigma with JS inverts sign, and the peak becomes negative. And if the magnetic field is perpendicular, there is no voltage because the cross product vanishes. So we use YAG to make this experiment to graphene. The YAG is grown on a substrate, GGG, and then we put by a sophisticated technique a graphene layer on top of the YAG film and two silver contacts, and we do ferromagnetic resonance of YAG with 9.4 gigahertz of frequency. The magnetization processes. This is the result of magnetization processes. This produces a spin current. I noticed that this slide is in Portuguese. I forgot to translate it. And then we measure the peak of the voltage produced by the charge current along the graphene layer. And this resulted from the conversion of the spin current into charge current by the Hashiba-Edelstein effect. We can do a simple calculation of the voltage, and from this we are able to extract the size of the Hashiba-Edelstein parameter. This was first published in 2015. The first author is our colleague from the University of Viçosa, Joaquim Mendes, who is very active. He interacts with many people, and he continued to do this work, and we published a more detailed paper a few years ago involving experiments done in the circuit to source in Campinas. Well, we also did, thanks to Joaquim initially, experiment with several other materials, like a topological insulator, this one here, tellurium, bismuth, and antimony, which was grown on a sapphire substrate. And then we do spin pumping experiments and we measure the voltage and we measure this as a function of the frequency, as a function of the intensity, and we're able to extract the Hash-Bedelsheim parameter. Actually, the film was grown at MIT in the group of Modera, actually. Here are some more results. I will skip this. Another topological insulator. Also did the experiment with a two-dimensional semiconductor, molybdenum sulfide. Again, this was made by Joaquim de Souza. He's able to obtain flakes of this material, and the flakes are placed on top of the egg, and with electrodes, and we measure the voltage by the spin pumping technique. The most recent one is in a wire semi-metal, thallium phosphide. Thallium phosphide can be grown by the flux method, and this was grown in Viçosa. In a wire semi-metal is a material in which two-dimensional electrons in two-dimensional conduction. They have bands that cross. In bands that cross, we have the formation of we have 2 points that have this band, a dispersion relation, electric dispersion relation, that has a V like this, and this is characteristic of a Dirac particle. And these Dirac particles, in some means, are wire particles, and this is a Dirac particle positive, and this is a negative Dirac particle. Well, it turns out that this also has the property of converting spin currents into charge current. The experiment was done by depositing a permalloy film on the thallium phosphide crystal. This is the FMR of the material. This is the voltage. It's not very beautiful like the previous ones. It's also not symmetric, but this was done in several powers and frequencies, and we confirm that this is conversion, the spin to charge conversion, and this is has a very large Rasch-Edelstein parameter, 0.3 nanometer. This is 100 times larger than graphene. And this has the size that can be eventually used. This is all at room temperature. All I'm showing here are measurement room temperature. So this is an efficient converter of spin current into charge current. This is almost accepted to be published in Advanced Materials Interface. Last result, we have some sample, let's say, that we put between the poles of the magnet, and we do some excitation. We apply a current, and we measure the voltage in the two terminals. For instance, we apply a current in the same device that I showed before, graphene on egg, and we vary the magnetic field. We also did this in molybdenum sulfide, and we observed a very interesting effect. The effect is this. Let's say that we apply a current here. This produces a two-dimensional current, charge, superficial, surface charge current in the 2D material. And this layer is in contact with the ferromagnetic material. Well, the charge current will produce a spin current by the Rasch-Edelstein effect. This spin current flows into the magnetic material. It produces a torque in the magnetic material. The torque will produce a counter spin current. The reflected spin current is converted into another charge current. And this charge current then adds the previous one. But the result is that this change in the resistance. This is also magnetoresistance. And one can show that the change in resistance proportional to the Rasch-Edelstein parameter. And we did this experiment, as I said, with graphene on the egg. And here is the result. We vary the magnetic field. So this is the change in the magnetization. This is the change in resistance. The change in resistance reflects the change in magnetization of the egg film, and also of the semiconductor, two-dimensional semiconductor. So this is the Rasch-Edelstein magnetoresistance. That was observed very recently, and this paper was published last year. In conclusion, Spintrônica is the field of science and technology that allows one to study the coupling of spins with electric charge, spin-optic effect, optical effect, electromagnetic application, spin band splitting, influence of thermal gradient. This is a figure that is shown in this recent paper by Dr. Hillebrand, and the spin current is opening new areas for research in physics and electronics. It's evolving rapidly. The number of publications are being increasing rapidly. There are several books written by several authors, but this is a textbook that I managed to write, was published last year. It's actually on magnonics. Magnonics is the field that studies magnons, the elementary excitation of magnetic materials. And the last chapter is Spintrônica. The last chapter is Spintrônica, which is an area that involves several of the effects that I showed. I have to show you this group, Antônio Azevedo, that I mentioned several times. Roberto Rodrigues, our Cuban colleague who works in Chile, Fernando Azevedo, José Holanda, that I mentioned, Joaquim Mendes in Viçosa. This is Recife, the Capibaribe River, Pacific Ocean here. As you all know, we are living very intense times and very tense times also, because in 8 days, the Brazilian population will be choosing a new government. And I hope very much that the new government is headed by Lula, because the person who is the president now is a crazy person. He's against science. He's against the truth. He's against the health of people. And we are terrified by the possibility of Bolsonaro being reelected. So in all talks that I've been giving the last weeks, I show this. I'm a professor and I am with Lula. Thank you very much for your attention.
Thank you, Sergio. A very nice, impressive talk. And congratulations for the last transparency. As you can recognize, I'm also with Lula. Okay, let's go further. I have to ask people. I just want to mention you that last Wednesday, Professor Jairo Roa Rojas from University of Nacional of Colombia in Bogota, he delivered a talk in Spintrônica in his proposal for a share in the Colombia Academia de Ciência. Now he's a share member. Congratulations to you, Professor Jairo. Okay, let's start.
Oi,
Jairo,
Albino. Estou aqui,
oi.
meu.
Parabéns.
Abraço para todos. Muito obrigado, muito obrigado. E eu queria não somente parabenizar o professor Rezende, mas também agradecer muito por essa aula que ele deu para nós hoje. Eu sempre falo nesses temas para os meus estudantes que eu espero estejam ligados hoje nessa palestra do professor Sergio, porque eu sempre falo para eles que é física exótica, porém não é mais exótica quando a gente escuta o professor Sergio. É uma aula de física extraordinária. Muito obrigado, professor. Eu tenho seguido o senhor nas redes, no LAU3M, na ALMA, que é a Associação Latino-Americana de Magnetismo, e sempre acabo aprendendo muitíssima coisa. Muito obrigado, professor, por essa palestra.
Muito obrigado a você, Jairo, e parabéns pela sua entrada na Academia Colombiana de Ciências.
Muito obrigado. Você não foi o meu professor, mas eu tenho aprendido muito do senhor.
Bom, depois eu faço um comentário. Later, I'll comment you about the proposal of Jairo. Okay, I would like to call Professor Ángel Bustamante, da Universidade Nacional Maior de São Marcos, decana das Américas. Ángel, go ahead.
Bom dia a todos. También a felicitar la palestra do profesor
Cámara,
Rezende.
Ángel. Por favor, cámara.
Cámara. Es que tenía problema con el... no está dando cierto mi máquina.
Okay, no hay problema. Go ahead.
Continua já.
Ángel, no hay problema. Puede continuar.
Un vídeo, pues está allá. Vamos a ver si ya ligó. Gustaría de agradecer la palestra del doctor Rezende. Tenía una curiosidad. Materiales topológicos, ellos se desenvolven por llevar corriente en la parte superficial. En caso de sus sistemas, la largura de donde se hace la topología, la corriente superficial, de cuántos angstroms o cuál es más o menos la medida de la parte superficial donde se desenvuelven las corrientes superficiales. ¿Usted tiene algún dato de esa referencia?
Ela pode ser estimada porque é possível fazer materiais com diferentes espessuras e você vê a mudança de comportamento, né?
Tá bem.
É da ordem de escala de nanômetro.
Yeah.
1 nanômetro ou mais.
Yeah.
Mais ou menos. Eu não gosto do nome isolante topológico, porque eu preferia o contrário, o nome é o contrário, o metal topológico, porque a topologia faz com que ele torne condutor. Eu não gosto do nome isolante topológico, mas esse nome foi dado e aí pode ser usado. Eu preferia condutor topológico do que isolante.
Foi dado para hacer más experto a matemáticas. Obrigado, profesor. Parabéns.
Obrigado, Ángel. Gracias. Bueno, me vamos a llamar ahora. Let's ask Professor Davi from Colombia. Professor Davi.
Me escuta, Albino? Dá para me...
Sim, sim. Claro, claro.
Obrigado, professor Sergio, pela excelente palestra. Eu sempre seguindo o senhor desde que escreveu o primeiro livro de ciência de materiais, estado sólido. Agora eu quero comprar o novo livro que o senhor mostrou aí. Professor Sergio, queria só fazer uma pergunta a respeito da importância das técnicas de crescimento físicas e químicas, a respeito da reproducibilidade, porque esses filmes são de alta qualidade, são filmes monocristalinos e com uma espessura bem controlada, né? Muito pequena. Então, eu queria saber quais são as novas tecnologias para pesquisa, né? Porque para aplicação tecnológica tem uma pesquisa muito avançada. Qual é a principais contribuições desde o ponto de vista de crescimento de filmes por técnicas químicas, por exemplo, e a importância em suas propriedades? Obrigado, professor. Um abraço.
Um abraço, Davi. Veja, as técnicas dependem muito dos materiais, né? Tem materiais que se consegue fazer por algumas técnicas e outros são melhores feitos por outras técnicas. Então, o material que nós trabalhamos muito é IEG, que eu mencionei, nitromargado. Até 10 anos atrás, ou menos até, aliás, desculpa, há 40 anos, IEG era feito pela técnica de Schokowski, uma técnica de bulk. Então, só se trabalhava com IEG bulk. E aí se desenvolveu a técnica de liquid phase epitaxy, que é uma técnica onde o líquido em alta temperatura está em contato com o substrato e aí, esfriando, aquele líquido vira um cristal. E conseguia-se fazer, então, um monocristal de boa qualidade fazendo LPE. E as primeiras vezes que se tentou fazer filme de IEG com técnica de filmes finos, por exemplo, sputtering, pulsed laser deposition, os filmes eram muito ruins. Mas, atualmente, se consegue fazer IEG por sputtering. Não é tão bom quanto o monocristal, mas como o IEG é um material excepcional, ele ainda é muito melhor do que outros materiais. Então, as técnicas dependem muito dos materiais. Então, alguns materiais são feitos por chemical vapor deposition. A técnica é importante, mas depende muito dos materiais. Então, o filme de grafeno que eu mencionei foi feito por CVD, Chemical Vapor Deposition, em cima de uma folha de cobre. E depois ela é transferida da folha de cobre para o material, para um outro substrato.
Professor, e uma coisa
Depende muito dos materiais.
Uma coisa adicional a respeito da aplicação. Na atualidade, a spintrônica está sendo utilizada para que tipo de dispositivo já aplicado a nível industrial, por favor?
Só dois. Só dois. Um deles é em cabeça de leitura de hard disk, que eu mencionei. E o outro é em memória de acesso aleatória. Qualquer computador tem uma memória de acesso aleatório que é feita de semicondutor. E há muito tempo as pessoas tentam fazer memória de acesso aleatório com material magnético, porque o material magnético grava a informação. Mas foram precisos 20 anos de tentativas muito diferentes, até que agora a Random Access Memory magnética, chama MRAM, estão comerciais, a Samsung está fazendo, e ela ainda é mais cara do que a do semicondutor. Mas a grande vantagem dela é que, se você sabe, no computador, a memória de acesso aleatório é usada para gravar informação de forma temporária. Eu estou usando aqui o notebook. Quando eu acabar de usar o notebook, para encerrar o uso, eu tenho que fazer o log-off, né? Quando eu faço isso, ele pega as informações que estão na memória de acesso aleatório e guarda no disco rígido. Isso demora um certo tempo. E quando eu vou ligar de novo, ele tem que buscar as informações todas de novo. Se eu tiver computador, já tem. Só com memória de acesso aleatório magnética, a gente, quando acabar de usar o computador, fecha ele desliga na hora. Quando abrir, ele volta onde estava anteriormente. Então, essa é uma segunda aplicação concreta. Agora, tem pessoas buscando muitas outras aplicações e tem pessoas prometendo muitas aplicações. As pessoas prometem aplicação para conseguir financiamento. Às vezes, não conseguem aplicação. Mas a perspectiva de muitas outras aplicações com funcionalidades diferentes das que existem atualmente. Mas, para resumir, só tem duas aplicações concretas até agora.
Obrigado, professor. Muito obrigado. Albino, obrigado pela oportunidade.
Obrigado, Davi. Thank you, Davi. Now we change continent. I will call Stuart home. Please, Stuart, go ahead.
Thank you. Thank you, Professor Rezende. Very interesting presentation. Thank you. I have some questions, just 2 questions on the spin Hall effect. So the proposal that was the original proposal from Diakonov and Perel, and then followed up by Hirsch, was an intrinsic effect, really spin orbit property of the material. Is it important to know whether your spin Hall effect is an intrinsic effect or an extrinsic effect? So if it was an extrinsic effect, it might be possible to say improve the size of the spin Hall effect, the spin Hall angle, to increase the efficiency of these types of devices. Is that important?
Stuart, as you said, there are intrinsic mechanisms and there are extrinsic mechanisms. People, for any effect, would like to have quantitative calculation of the effect. So people calculate both. And in some materials, it's clear that the extrinsic effects are stronger than the intrinsic effects. The system that has shown the largest spin Hall angle, nearly 0.5, 50%, is a material made of platinum with nanoscopic particles of silver and another platinum layer on top. It's the nanoscopic effect, the collision at the surface of the nanoscopic particles that makes the spin Hall angle large. So as I said, both are important, and people, the theoreticians would like to do a calculation and compare the calculation with the experiment. So normally you have to calculate both, and there are theories for both.
I tried to measure the spin Hall effect electrically in gallium arsenide, and it's very, very difficult. You can try and put some doping in and change the size, but you're always competing with a very, very well-defined charge Hall.
Yeah.
My other question is, do you see any applications for spin Hall effect? I mean, we have applications for, say, GMR, TMR. They've really brought in the memory industry has really benefited tremendously. Do you see any applications for spin Hall effect devices?
Look, the MRAM derivation, the structure that has become the most important uses the planar effect. Current in the plane in a material that has strong spin-orbit coupling produces a charge current that goes and go through the spin valve, for instance. So the spin Hall effect is there. Spin Hall effect is there because it has to convert a charge current into a spin current. The charge current in the plane produces a normal spin current by the spin Hall effect. And this is the mechanism that is important in the MRAM.
In MRAM, so it's already, the applications are already there. Yeah.
Yeah.
Thank you. Thank you. Very, very interesting talk. Thank you again.
Thank you.
Thank you, Sport. Agora nós movemos para a nossa querida América Latina e me vou a chamar professor José Fermín. Fermín, are you there? Está allá, hombre?
Estou.
Sí.
Sérgio, muito bom, né, ter você de novo aqui, hein? Pela segunda vez no ano a gente se encontra. Sim, eu tenho uma pergunta. I have a question because there are some participants in this network that maybe don't understand language. I try to speak some naive English. Sergio, after you talk about spin voltage, yes, induced by spin current. After that, I could not avoid to think about some resistive effect in the spin material. If that's so, how can you control those resistive effects?
How can you control resistive effect?
Yes.
Because the resistance,
Yes.
the resistance depends on the collision.
Okay. Oh, yes.
If the collision, the collision system involves somehow the spin-orbit coupling, then this is how the spin will change, the state of the spin will change the resistance.
So technically, the spin current and the spin voltage does not satisfy Ohm's law.
Satisfies Ohm's law. Perhaps I did not understand well your question, but the fact is that the resistance has several effects. Once you have the resistance, D is equal to I times R. But this R, the resistance, depends on the spin.
So, yes, I understand. So there are some resistive effects.
Yes.
Yes, okay. That's all. Sergio, ¿você lembra isso aqui?
Lembro. Ele tem inglês agora também.
Isso aqui você me deu aquela vez. Sérgio, muito obrigado. Tomara aí que possa se encontrar dia desses lá em Recife e tomar café lá com o Albino na praia.
Vamos. Prazer em vê-lo, Sergio.
Café não, caipirinha.
Gracias, Sergio. The next edition will be in Spanish. Yeah? It's okay, Sergio? Okay. Now I would like to call Professor Arturo Martínez, de Cinvestar, in Mexico. Arturo? Arturo? ¿Estás ahí, hombre? Bueno. Bom. Me deixe agora chamar o professor Isaías de Oliveira. Isaías? Olá. Muito bem. Parabéns pela camisa.
Isaías está sem som.
Não escuto.
Precisa una cachaza.
Isaías, não tem som.
Micrófono.
Mientras arregla, puede pasar a otro panelista.
Sí. Luis, ¿tienes preguntas?
Nosotros ahora estamos tentando, profesor Rezende, con un grupo de profesor Ángel Bustamante en la Universidad de San Marcos y también con un grupo en Cambridge y con la ayuda de Stuart Holmes, hacer unas capas multilayers de YBCO IPCO, superconductor IPCO, con una capa de níquel ferromagnético. Ahora estamos tentando hacer device, ya estamos logrando más, tenemos ahora problemas con contactos para hacer las medidas eléctricas. Más, señor, ¿qué espera que encontremos cuando haya esta interacción superconductor diamagnético en el estado superconductor con una capa antiferromagnética? Si hay una competencia y cómo afectaría si es que los vórtices. Nosotros esperamos que vaya a ser dependiendo de la dirección, va a afectar a la formación de vórtices y también va a afectar, digamos, ese campo magnético generado en la capa de níquel, va de cierta manera a influenciar en el efecto Meissner y en el comportamiento magnético del superconductor. O señor ha intentado más o menos también ver a una experiencia. Nosotros no hemos encontrado literatura al respecto, más si el señor más o menos de acuerdo a su experiencia, ¿qué más o menos podrías hacer? Porque he visto en una de sus transparencias, o señor, que presentó ahora, es que hay algunas también similares, pero no en superconductores, sino en otros materiales abaixo, en la primera capa.
Você falou, numa certa hora, um material antiferromagnético. Mas níquel é ferromagnético. Níquel é ferromagnético.
Sí.
O ferromagnetismo do níquel, ele certamente vai interferir com a supercondutividade. Agora, eu sei que materiais supercondutores também têm corrente de spin, né? Tem corrente de spin. Realmente não tenho experiência em supercondutividade para prever o que eu espero. Eu não sei o que eu espero. Não sei.
Sim. Mas não é
certamente, ainda há muita coisa a ser explorada no sistema supercondutor. Pouquíssimos trabalhos. Então, vai ser interessante ver o que vocês observam. Mas eu confesso que eu não sei o que esperar.
Nosotros, el sistema parece ser simple, mas es muy complejo porque debajo de la temperatura crítica es superconductor y diamagnético, y arriba antiferromagnético, el IPCO. Ahí habría una competencia antiferromagnético con ferromagnético del níquel. Y ahora el níquel, arriba también no hay, se genera un níquel oxide, que ese níquel oxide es antiferromagnético. Entonces hay una competencia de muchos multilayers ahí, ¿no? Quisiera aprovechar también, profesor Rezende, antes de continuar con las siguientes panelistas, que ahí o público está preguntando si o señor puede compartir sus transparencias en PPT o en PDF, como señor, o no, si nos puede enviar, por favor, a la red, ¿no?
O PPT é muito longo, mas o PDF
Perfeito.
Tem muita animação, o PDF acho que serve, e eu vou mandar para Albino por e-mail.
Sí, también. Perfecto, obrigado. También quisiera mencionar rápidamente unas noticias de la red, que el journal oficial de este ciclo de conferencias de la red de las MAT es el Heat Treatments and Surface Engineering, que es de Taylor and Francis. Y el profesor Albino recientemente, y el profesor Arturo Martínez del Sinvestal de México son ahora editors de ese journal. Bien, pasamos entonces ahora a los siguientes panelistas. Ok, Albino.
Gracias, Luis. Bueno, ahora me voy a llamar a Sergio, profesor Sergio Conejero. Sergio.
Hola, ¿qué tal?
Adelante, hombre.
Bueno, buenas tardes, aquí son las 12. Yo tengo una pregunta muy interesante su charla por lo demás, profesor Rezende. Realmente la disfruté mucho. Aprendí varias cosas que no sabía. Usted habló sobre el fosfuro de tantalo, el fosfuro tantalo y el arsenurio de tantalo. Estos dos compuestos tienen ese comportamiento de semimetal tipo Will, que es bastante interesante. En realidad, yo he leído muchos sobre eso debido a que estos materiales se caracterizan por hacer una buena conversión de luz o de fotones en electricidad. Me gustaría saber la elección, por qué eligió usted fosfuro de tantalo y no arsenuro de tantalo, y si estos dos compuestos efectivamente tienen las mismas propiedades o no.
Sérgio, o paper que mostrou que o fosfato de tântalo é um semimetal wire, é um paper publicado na Nature Communication, uma revista Nature, em 2015. Ou seja, tudo é muito recente. E isso fez com que muitas pessoas procurassem fazer experimentos envolvendo esse material, que não é difícil de crescer. Ele cresce, como eu falei, pelo método de fluxo. Agora, você mencionou um outro que eu não conheço as propriedades.
Ok, el arsenuro de tantalo o tantalum arsenite is similar to the...
Sim. Eu não sei. Não,
Ok.
Não tenho essa informação.
Ok, muchas gracias.
Gracias, Sérgio Conerreiro. Seu xará, Sérgio. Bueno, agora nós vamos perguntar ao público de Colômbia. Eliana, temos perguntas do público de Colômbia?
La pregunta es de Juliana Rivera. Ella dejó la pregunta en inglés, entonces, bueno, la voy a leer en inglés. She is working with a TMIG sample. She's doing ferromagnetic resonance measurements. The compensation temperature of this ferromagnetic is 135 Kelvin. The question is, what could be the behavior you expect from the resonance near to this temperature? Would you find signal? That is the question from this study.
The resonance signal changes a lot across the transition. You said that it's a compensation temperature.
Mm-hmm.
So I understand that it is paramagnetic above and ferromagnetic or magnetic below. So the signal is much stronger in the ordered magnetic field, much stronger than in paramagnetic field.
Thanks a lot, Professor. Thank you. Well, that is the question from the public. Thanks a lot for this opportunity. The students from of the Professor Jairo Roa and David Landines, we were connected here enjoying this talk. We really learned a lot. Thanks a lot.
I'm sorry, Eliana, I did not understand the question.
Thank you.
Eliana, can you repeat, please?
Maybe in Spanish.
En español. Sí. Lo siento. Muchas gracias por la charla. Los estudiantes del profesor Jairo Roa y David Landines estuvimos conectados aprendiendo muchísimo sobre todo este tema. Muchas gracias. No tenemos más preguntas.
Sim. Muito obrigado.
Gracias, Eliana. Ahora vamos a llamar Ximena. Ximena.
Buenos días, profesor Albino, y buenos días, otro profesor. No, por este lado no tenemos preguntas. Hay varios estudiantes que agradecen por la charla, ya que varios de los estudiantes de acá pues estamos trabajando precisamente en la parte de materiales que puede llegar a ser aplicados a este proceso de Spintrônica. Entonces, muchísimas gracias por la charla.
I think there is no other questions around. So I am obliged by the General Secretary to make propaganda, some broadcasting of the network. So here we go. esta é uma rede que se destina a poner as pessoas juntas para discutir ciência. É a Rede Latino-Americana de Física de la Matéria Condensada e Ciências de Materiais. É composta por algumas universidades, a Universidade Nacional Maior de São Marcos, que é a decana das Américas, e a Universidade de Barranca, em Peru, a Universidade Nacional de Colômbia, em Bogotá, em Barranquilla, e a Universidade do Norte, em Colômbia, a Universidade Zulia, em Venezuela, a Universidade Federal Rural de Rio de Janeiro, a Universidade Federal do Pernambuco, as duas no Brasil, o CIVESTAF no México, o Centro de Investigação de Materiais Avançados também no México, a Universidade San Sebastián em Porto Montt, Chile, a Universidade Católica do Norte em Antofagasta, em Chile, e a Universidade College London e University of Cambridge, em UK. Bueno, propaganda foi feita. Veio aqui que Isaías está. Consegue falar, homem?
Vocês conseguem me ouvir?
Sim, sim.
Então, só queria agradecer ao professor Sergio Rezende, nosso ex-ministro da Ciência e Tecnologia, no momento mais próspero que a ciência brasileira teve, desde que eu estou em ciência, há 30 anos. E o meu desejo é que no próximo domingo a gente confirme aquele número ali, 13, e que o Sergio Rezende seja não o último ministro da Ciência e Tecnologia, mas o próximo. Eu gostaria só de fazer um comentário em termos de ciência, foi a pergunta do Luiz, o Luiz Valadares. É que quando você trabalha com supercondutores e você divide, por exemplo, spin Hall effect, na essência, os pares de Cooper, eles têm spin up e down. Então, quando você faz a divisão deles, pelo menos você vai quebrar os pares de Cooper. Então, você vai ter, no efeito spin Hall effect, desculpa, no efeito de spin Hall effect, você quebraria os pares de Cooper, quebrando assim a supercondutividade, mas isso tem que ser visto agora para os supercondutores de mais alta temperatura, que podem haver outros mecanismos. Mas, certamente, nos de baixas temperaturas, aqueles que são governados pela BCS, isso certamente o spin Hall effect deve quebrar a supercondutividade quando você divide spin up e spin down. Bom, mas eu gostaria só de agradecer mais uma vez a sua palestra e deixar aqui um agradecimento musical com a Pífana de Pernambuco.
O som sumiu.
Puta merda. Logo agora.
Um frego.
Bueno, hombre, yo tengo dos comentarios. Uno es que lo público, y en especial o professor Ángel Bustamante, me pedem para agradecer a Sérgio a disponibilidade de enviar as transparências em PDF. E segundo, Isaías ainda está aí, eu tenho que fazer uma correção. Como diz um amigo nosso, nunca na história do Brasil teve um ministro de Ciência e Tecnologia tão bom. Sérgio sempre será nosso ministro de Ciência e Tecnologia.
Tá bom.
Muda a volta.
Grande abraço para vocês todos.
Sérgio, você fica à disposição de suas últimas palavras, mais algum comentário, e depois a gente passa para o secretário-geral. É com você, Sérgio.
Não tem mais nada a acrescentar, já falei aí durante muito tempo. Eu só tenho que agradecer a vocês a paciência por estar aqui conosco esse tempo todo e, se houver oportunidade, no futuro, de uma interação científica em alguma dessas áreas, eu estarei à disposição. Obrigado a vocês, a todos, pela audiência. Tchau.
Olha, antes de você sair, vamos passar a Luiz, o secretário-geral, e vamos pedir a todos que abram a câmera para a gente despedir do professor Sérgio oportunamente. Luiz, suas palavras.
Obrigado, profesor Sergio Rezende, por su interesante palestra. Profesor Sergio Rezende, todos los sábados nosotros organizamos, esta red organiza a la misma hora palestras de investigadores latinoamericanos o europeos alrededor del mundo que muestran sus avances y para hacer luego colaboraciones con universidades latinoamericanas. Los latinoamericanos muestran sus avances, etc. O señor está convidado a que siempre participe los sábados en las palestras que el señor desee y crea que es de su interés. Las palestras siguientes van a ser, por ejemplo, el día 29 de octubre, José Luis Ochoa, del Instituto Venezolano de Investigaciones Científicas. Su palestra es titulada Propiedades eléctricas y modelos de percolación aplicados a mezclas, conductor aislante. Y el moderador será el profesor José Fermín, de Venezuela, de la Universidad de Zulia. El 5 de noviembre, el sábado 5 de noviembre, la palestra será del doctor Adrian Ionescu, de la Universidad de Cambridge, y está titulada su palestra A Voyage from Bulk via Thin Films and Nanoparticles to Surface Magnetism. Su palestra es del doctor Adrian Ionescu, va a empezar a las 9 de la mañana, hora de Perú, 11 de la mañana, hora de Brasil. El noviembre 12, la palestra será del profesor Diego Lamas, de Argentina, y el profesor David Landinés Telles será el moderador. El 19 de noviembre, Edson Sardela, el profesor Isaías González Oliveira será el moderador. El 26 de noviembre, Sergio Conejeros Espindola, de la Universidad Antofagasta de Chile, y el moderador será el profesor Arturo Martínez. El 3 de diciembre, la palestra de Leopoldo Suescún, de Uruguay. El moderador será el profesor David Landinés. El 10 de diciembre, Alexander Polasek, y el moderador será Isaías González Oliveira. Finalmente, la última palestra de este año es el 17 de diciembre con Carlos Santos, de la USPI, y el profesor Albino Aguiar será un moderador. Bien, Sergio. Muchas gracias. Nosotros abrimos nuestras cámaras todos. Open your cameras, everybody, to say goodbye to Sergio Rezende, and thank you very much for all that. And we also listen the frego from Isaías.
Obrigado, Sérgio. Sérgio, abraço a todo mundo. Comentário para você, o Albino e o Isaías lá. Aqui tem um pessoal do Departamento de Estatística que está acompanhando muito de perto as suas eleições.
Sim. Vamos lá, dia 30.
Vamos lá, dia 30.
O pessoal está torcendo pelo Lulão.
Tá bom. Obrigado. Abraço,
abraço a todos.
Até sábado.
Tchau.
Obrigado, Sérgio. Um abraço. Tchau.
Obrigado.
Ciao. Thank you.
Hasta la próxima.
Goodbye to everybody.
Bye. Arrivederci.
Bye, everybody.
Arrivederci.
Ciao.
Thank you very much.
Thank you.
Thank you very much for this.